Let's identify all the points of inflection of that and determine the intervals where the function is concave up or concave down, similar to a previous problem we've done. So let's jump in. What color did I use on that other problem? Not that it impacts your life. I think I used black, so we'll do that. Let's find the derivative. We'll bring it over here just so we'll save some space. 4x cubed minus 12x squared. Fantastic, okay. We're going to set it equal to 0. No, they're asking about points of inflection and concavity. That is a second derivative issue. So 12x squared minus 24x. Yay! Now we'll set this equal to 0, and we'll factor out 12x. That gives us x minus 2. So x equals 0 and 2. Unless I have done something wrong. Second guessing myself. Nope, I think I'm good. All right, so let's do the little number line thing. 0 to 2. I'm going to plug numbers into the second derivative, not the first derivative. And I'll plug in a negative. Any negative will do. Negative here and a negative here give me a positive second derivative. Plug in a 1, positive, negative. That gives me a negative. And plug in a positive here. That's going to give me a positive. There we go. All right, so that's what we're looking at. And we need to find out where we have a point of inflection, or more than one point of inflection. And a point of inflection, a little bit of vocabulary, is where the concavity changes. It's where the derivative equals 0 or does not exist. But the concavity also has to change, okay? So for example, if I would have done this, and I would have ended up with something different. Let's doodle for just a second. If I would have had this and this and this and 0 and 2, and I would have ended up with f double prime is positive, f double prime is positive, f double prime is negative. I would have a point of inflection here because the concavity would change. I would not here because the concavity would not change. We've gone from concave up to concave up. Well, that's not really a transition now, is it? There we go. So in order for us to have a true point of inflection, we have to have a change in concavity. We're going to have a change in the sign in that surrounding area, and the derivative equals 0 or doesn't. Second derivative equals 0 or doesn't exist. Okay, back on track. So we have a point of inflection, 2 points of inflection. We have points of inflection at x equals 0 and at 2. And we are going to have concave down. Oh, let's just abbreviate. Concave down, C down, I can do it that way, at the interval from 0 to 2. And concave up, looks like cup, from negative infinity to 0, oops, along with 2 to infinity. Technically, that word would be or. All right, we're about to use the second derivative test, which we just discussed in the previous video, very end of that video. Use the same function as the previous problem. Use the second derivative test to determine if each critical point, pause right there, find your critical points. Find your critical points. That's where the first derivative, which we've already found, equals 0. Determine if each critical point corresponds to a maximum, a minimum, or neither. So let's do this. We're going to set this equal to 0. Solve for x squared is our greatest common factor. That gives us x minus 3 right here. So x equals 0 and 3, which kind of makes sense. There's a minimum there, and there's a place where the derivative equals 0. You can see where the slope levels off to 0 right there. Just kind of goes, levels off. So we have a couple critical points, but I need to know if they're maximums or minimums or neither. And I think it's obvious from the graph we have a minimum here and we have a neither here. But let's use the second derivative test. So at x equals 0, the first derivative equals 0, and the second derivative is, okay, the second derivative is also 0. Okay, at 0, the second derivative is 0. That's where this came from in the first place. The test fails. From the graph, we know this point is neither. And this is a really good indication that generally, in my head right now, I can't think of an exception to where you would ever have a maximum or a minimum where the test fails. So this would be neither. Okay. So x equals 0 is neither. All right. At x equals 3, the first derivative is, all right, oh, wait, looking in the wrong place. The first derivative is equal to 0. That's what we just found. Sorry. I'm back up here. This is the first derivative. Here's the second. The second derivative is positive, and therefore x equals 3 corresponds to a, all right, maximum, minimum. Let's see. Now, obviously it's a minimum, but let's think about it logically. The first derivative equals 0, and the second derivative is positive. We're in this situation right here. We have a concave up, so it must be a minimum. Corresponds to a minimum.